Welcome to the debate. So picture 80,000 kilograms of, aluminum, cargo, and jet fuel just hurling down a concrete strip.
Right.
Your airspeed is rapidly ticking upward. You accelerate past 100 knots. The end of the runway is quickly approaching, and you are just 20 knots below V1, which is the absolute maximum speed where you can safely initiate a rejected takeoff.
The absolute point of no return.
Exactly. The kinetic energy you've built up is just massive. And then, suddenly, a cascade of alarms floods the flight deck. A master warning sounds. The screens flicker. Systems drop offline one by one. You have just suffered an electric emergency configuration, an ELEC EMR config.
Which is every pilot's worst nightmare.
It really is. In this terrifying high-speed regime, you face the ultimate aviator's dilemma. For the student pilots listening, the question is, do you abort the takeoff because critical aircraft systems have just failed, or do you continue into the air with a severely degraded airplane? I take the position that continuing the takeoff is the absolute safest and, frankly, the only viable option here, because the specific combination of mechanical failures makes a high-speed stop physically impossible without a catastrophic runway excursion.
Well, I come at it from a completely different way. Taking a crippled aircraft into the air right at the critical moment of rotation carries immense, unquantifiable risk. If we look at the actual flight manuals, the activation of this specific ECAM alert, the Electronic Centralized Aircraft Monitor, provides the technical justification for the captain to execute a rejected takeoff prior to V1. You have the runway, and you have the authority to use it.
To really get to the bottom of this, though, we need to move past the procedural textbook definition of an abort and look at the raw physics of stopping. When you lose your electrical systems to this degree, a full ELC EMR config, you suffer a complete, catastrophic loss of your primary deceleration systems. The braking and steering control unit, the BSCU, goes entirely dark.
Right. And that loss is significant. The BSCU is essentially the brain behind the wheels.
Exactly. Without it, you have zero normal braking, zero anti-skid, and zero nose wheel steering. But it doesn't stop there. Your thrust reversers are completely unavailable. And to make matters worse, half of your ground spoilers, specifically spoilers 1, 2, and 5, are just completely inoperative.
Which, obviously, severely impacts aerodynamic braking.
It impacts aerodynamic braking, sure, but more importantly, it prevents the transfer of the aircraft's weight off the wings and onto the landing gear. I mean, we have to explain the mechanism here for the audience. Brakes stop the wheels, but friction with the runway stops the airplane.
Right.
If those spoilers don't deploy to kill the lift over the wings, the aircraft still wants to fly. The weight hasn't settled onto the tires. Without weight on the wheels, your brakes can't do their job even if they were working perfectly. Trying to stop a heavy aircraft from V1 minus 20 knots without that weight transfer is essentially a guaranteed severe runway excursion. The math simply does not support staying on the ground.
That's a compelling argument. But have you considered the environment inside the flight deck at that exact second? We have to look at what continuing the takeoff actually means. You aren't just continuing a normal flight. You are intentionally taking an aircraft into the sky that has reverted to alternate law for its flight controls.
True, but...
And the first officer's display units are entirely lost. They are staring at blank screens. The cognitive load on that crew is instantly pushed to the absolute maximum.
It's a high workload. Absolutely, I agree with that.
But it's more than just a high workload. It's an explicitly authorized abort condition. The flight manual states that the activation of any ECAM alert is technically one of the few justifications for a high-speed rejected takeoff. The manual doesn't say, except for an ELEC EM config.
No, it doesn't.
Right, so at 20 knots below V1, the aircraft is legally and technically within the abort envelope, forcing a crew to transition from a high-speed ground roll into a highly dynamic flight environment, flying a crippled aircraft with half the cockpit completely dark. I mean, that is a massive hazard in its own right. The risks of flying this degraded machine are so severe that the manual preserves the captain's right to put the brakes on.
I see why you think that, but let me give you a different perspective on what putting the brakes on actually looks like in this specific emergency. Because the BSCU is dead, the only braking you have left is alternate braking, which is supplied entirely by the yellow hydraulic accumulator.
Right, the backup pressure system.
Yeah, the backup. But we need to talk about how limited that backup is. That accumulator limits your brake pressure to a maximum of just 1,000 psi. Even worse, it only holds enough pressure for a mere 7 full brake applications. I'm trying to picture the exact physics of what the pilot is dealing with here. It sounds essentially like driving a fully loaded semi-truck down a steep mountain pass, and suddenly your main air brakes fail. You're left with just an emergency handbrake.
That's a fair visualization. You have a purely mechanical backup with finite energy.
Right, a handbrake that you can only pump 7 times before the pressure is completely gone. But crucially, and this is the terrifying part, you have no anti-skid system on that handbrake.
Ah, yes.
If a pilot applies those 7 applications of 1,000 psi while moving at 130 knots, without a computer to rapidly pump the brakes and prevent a skid, the tires will simply lock up.
They will lock, yes, which means the pilot has to manually modulate the pressure with their feet.
But human feet cannot replicate an anti-skid computer. At those speeds, locked tires don't just skid. The friction generates so much intense heat that the rubber melts. It literally creates a liquid layer of molten rubber between the tire and the runway. You drop into a state of zero friction.
Wow.
The tires blow out almost instantly. You essentially turn an 80,000 kilogram aircraft into a high-speed sled. And remember, you have no nose wheel steering to keep it on the center line. The physics of the situation dictate that the aircraft is going off the runway.
I'm sorry, but I just don't buy that it's a guaranteed disaster. Let me tell you why. I am not denying the reality of the yellow accumulator's limitations, or the loss of anti-skid, or the fact that stopping is incredibly perilous.
It's beyond perilous.
But we have to look at the manual's underlying logic. If the stopping capability was truly zero, if a runway excursion was a guaranteed, fatal event in every single scenario, the engineers would have categorized this failure as a hard, do not abort condition. It would be hard-coded into the high-speed regime philosophy. But it isn't.
Well, because they can't account for every single variable.
Exactly. The manual trusts the captain to weigh the specific reality of their runway against the emergency. Imagine departing from a massive runway like Denver International, which is, 16,000 feet long?
Right, it's huge.
You might have 10,000 feet of pavement remaining ahead of you at V1-20. A skilled captain applying careful, incrementally modulated pressure to that yellow accumulator has the authority to keep that aircraft on the ground. Why? Because they recognize the sheer terror and the aerodynamic fragility of taking an alternate law aircraft into the sky with a blind first officer. You have the pavement, you use the pavement.
That's an interesting point, though I would frame it differently. The manual doesn't forbid it outright, precisely because of those rare, infinite variables like a 16,000-foot runway. But we have to acknowledge how heavily the manual guides the pilot's psychology. The core of the high-speed regime philosophy is that once the aircraft is well above 100 knots, the crew must be go-minded.
Go-minded, yes, but not go-blinded.
Very clever. But the kinetic energy at that speed requires an overwhelming reason to abort. The manual specifically defines rejecting a takeoff near V1 as a more serious matter that directly could lead to a hazardous situation. And let's revisit the lack of thrust reversers.
Okay.
Reversers are the only deceleration force that does not rely on runway friction. They work by redirecting engine thrust forward. Without them, and without spoilers to dump the lift, you are relying entirely on the friction of tires that are highly likely to melt or blow. Being go-minded isn't just a psychological suggestion. It is a profound aerodynamic reality. Above 100 knots, this specific aircraft is eager to fly, and it is physically incapable of safely stopping on a standard runway.
Okay, let's talk about the reality of that eagerness to fly. I want to detail exactly what happens at the moment of rotation, VR. Launching into the air with an electric emergency configuration is equally, if not vastly more dangerous than a low-speed runway overrun.
I completely disagree.
Hear me out. At VR, the pilot pulls back on the side stick to lift the nose. In normal operations, in normal law, the aircraft's computers are basically wrapping the plane in an invisible protective bubble.
the flight envelope protections.
Right. The computer prevents you from overpitching and striking the tail on the concrete. It prevents you from pulling back so hard that you exceed the critical angle of attack and stall the wing. But in ELE EMR config, you instantly drop into alternate law. That protective bubble pops. Those pitch protections are completely gone. Those roll protections are gone. You are flying raw aerodynamics right at the very boundary of the aircraft's lift capability.
But the aircraft is still fundamentally stable. Alternate law doesn't mean the plane just falls out of the sky.
It doesn't fall out of the sky on its own, but we have to factor in the human being flying it and the environment they are suddenly plunged into. The first officer is practically blind. Their primary flight display, the PFD, is dead. Their navigation display, the ND, is dead.
Yeah, they lose a lot of situational awareness.
Completely. Normally, the first officer is monitoring the pitch rate, calling out speeds, acting as the critical second set of eyes. That's gone. The captain is now flying the aircraft solely on PFD1 and ND1 alongside the engine warning display, while a piercing master warning chime is continuously blaring in their ears.
It is a massive sensory shock, I grant you that.
It's sensory deprivation mixed with sensory overload. We have to talk about how spatial disorientation works. When you accelerate and rotate into the night sky or into clouds, your inner ear plays tricks on you. It's called the somatogravic illusion.
Right, where you feel like you're pitching up.
Exactly. The acceleration makes your brain feel like the aircraft is pitching up much higher than it actually is. In normal law, the computer stops you from reacting incorrectly. In alternate law, navigating that exact second of rotation is incredibly fragile. The startle factor alone is immense. The pilot is reacting to a blaring chime, screens going dark, and a sudden change in how the stick physically feels. One slight overcorrection induced by that illusion, and you stall the aircraft at 50 feet. I argue that a stall at 50 feet is vastly more dangerous than sliding off the end of a runway into a clearway or an engineered arrestor pad.
I'm just not convinced by that line of reasoning because you are vastly overstating the fragility of the aircraft in alternate law and underestimating the strategic options available to a crew once they actually get airborne.
How so? The protections are gone.
The hard envelope protections are gone, yes, but the aircraft does not suddenly become an unmanageable bucking bronco. It handles very much like a conventional airplane. A pilot with good foundational stick and rudder skills can fly an Airbus in alternate law. Let's outline the mechanics of what happens if you safely transition to flight.
Okay.
The aircraft still has fully operating, perfectly healthy engines. It has intact essential navigation and communication. The captain's PFD1 and VHF radio are functioning perfectly. Once you pull back on the stick and leave the runway, you instantly buy yourself the most valuable resource in aviation.
Which is?
Time. You can climb to a safe altitude. You can establish a holding pattern. You can silence the master warning, take a breath, and calmly run the ECAM procedures in a safe, open airspace.
But you are assuming you make it to that safe altitude cleanly. You are treating the transition to the air as a procedural certainty. You are assuming the startle factor of a completely dark right side of the cockpit combined with the loss of pitch protection doesn't result in a fatal handling error during the 3 most critical seconds of the flight.
I am assuming it because flight crews are trained extensively for exactly that transition. We actually have a direct parallel found right in the flight manuals to support this airborne strategy. Consider Airbus's philosophy on high-speed tire failures.
Okay, the tire blowout procedure.
Right. When a tire blows near V1, the philosophy is absolutely not to slam on the brakes. If you do, you risk tearing the landing gear completely off the aircraft. The safest, most strategic action taught to every pilot is to get airborne. Why? Because the air is safe. Once you sort out the emergency in the air, you can hold, you can burn off fuel to significantly reduce your landing weight, and then you return to land.
And I can see that having the full runway upon return is ideal.
It is more than ideal, it is the only way to manage that degraded yellow accumulator braking system. When you return to land, you have the absolute maximum full runway length ahead of you.
You can touch down precisely at the beginning of the threshold. Now you have 10,000 feet to carefully incrementally use those 7 applications of the handbrake without anti-skid. You can let aerodynamic drag slow you down naturally before you even touch the brakes. You have margin. If you abort the takeoff at V1 minus 20 knots, you have 0 margin.
It absolutely gives you the margin to manage the braking later, yes. But my core contention remains that getting to that safe altitude is an extreme human factors challenge. The lack of flight control protections right at liftoff means any pilot error could be fatal. You say time is the most valuable resource, but you don't have time during the rotation phase.
Well, you have your training.
You have milliseconds to react to a massive, disorienting shock to the flight deck. The first officer can't even read the emergency checklists properly on their dead screens to assist the captain.
It requires excellent crew resource management, certainly.
It requires perfection in a moment of sheer chaos. If the captain decides in that split second that the sensory overload, the loss of instruments, and the degradation of the flight controls are simply too much to guarantee a safe climb-out, the ECAM alert remains a valid technical justification to abort before V1. The manual preserves the captain's right to abort precisely for this reason. You look at the runway ahead of you and you choose the physics of the ground over the unpredictability of the air. A runway excursion at low speed at the end of the pavement is highly survivable. Aircraft are designed to absorb that impact. A stall or loss of control at 200 feet is not survivable.
But the ground is governed by inflexible, brutal laws of physics. Kinetic energy increases with the square of your speed. At 130 knots, you carry a terrifying amount of energy. To summarize my position, flying an aircraft in alternate law with partial instrumentation is a daunting task, I will grant you that. It demands a cool head and precise flying. But it is a manageable trained piloting task. The aircraft, fundamentally, wants to fly.
Right.
Conversely, trying to stop an 80,000-kilogram machine without anti-skid, without steering, without thrust reversers, and without half your ground spoilers on a rapidly shrinking runway is a physical impossibility. No amount of pilot skill or captain's authority can manifest runway friction out of thin air when the tires have melted. By continuing the takeoff, you translate a guaranteed physical catastrophe into a manageable human factors challenge.
And to summarize my position, while stopping under these severe mechanical limitations is incredibly perilous, the manuals explicitly preserve the captain's authority to make that choice. Why? Because an electric emergency configuration severely degrades the aircraft's flyability and entirely blindfolds half the flight deck at the most dangerous phase of flight. Forcing a transition into the air without envelope protections while experiencing massive sensory disorientation is an extreme, unquantifiable hazard. The manuals trust the pilot's judgment over a blanket assumption that the air is always safer.
It is a profound, terrifying moment of decision-making. What this scenario really illuminates is how aviation pushes human beings to balance aerodynamic theory with human psychology in these split-second windows.
Of stopping a heavy machine with no brakes, and the fragile aerodynamics of forcing a degraded aircraft into the sky while half blind.
There is so much more to explore regarding how flight systems are designed to mitigate these massive failures, and how crews train to overcome their own sensory illusions. It really leaves you wondering, when the master warning sounds and the runway is disappearing beneath you, which risk would you choose to accept? The decision rests entirely on the shoulders of the crew.